The new unit that we're going to start today is called electromagnetic radiation. Today we're going to spend some time talking about the types of EMR. We're also going to talk about how EMR is produced, what it consists of. Generally, we say that EMR is energy. It is pure energy that travels in a wave-like form. Energy that travels through space, but that energy that can travel through nothingness of space, but also can travel through air or water or glass as well. It's pure energy that travels in a wave-like form through just about anything. What does it consist of? Well, I'm going to show you a diagram here. I'm not going to ask you to copy this diagram yet, because I want you to understand exactly how this diagram is drawn first. This is a picture of what EMR would look like if you could see the nature, the fundamental nature of EMR. It consists of two fields, an electric field and a magnetic field. We're going to say the electric field is on the y-axis here, and we'll make that in blue. So the electric field would look something like this, if you can follow my hand here. The electric field would look something like this. A sinusoidal wave on, in this case, the y-axis. It doesn't have to be the y-axis, by the way, but in this case, it is on the y-axis. Electric field, sinusoidal wave on the y-axis. There is, at the same time, and in phase, what I mean by in phase is when you have a crest of one, you have a crest with another. In phase with that sinusoidal electric field on the y-axis, okay, you have a sinusoidal magnetic field on the z-axis. So it goes horizontally like this. Now, it's hard to draw this, but if you understand what I'm trying to say, the diagram tends to make a little bit more sense. Follow my fingers again. I'll try to do both of them at once. And this is hard, by the way. You try it if you don't believe me. Okay, here's the electric field on the y-axis. Here's the magnetic field on the z-axis. Okay, what you got is this. Two crests and then two troughs. Two crests and two troughs. You've got an electric field and a magnetic field, both sinusoidal in nature, perpendicular to each other, in phase with each other, traveling perpendicular to both of the waves. Notice that? Okay. One wave is like this. Okay. One wave is on the x-axis. One wave is on the y-axis. Sorry, the y-axis and z-axis. Which way is it traveling? Along the x-axis. It's traveling perpendicular to both of those waves. So perpendicular is a big thing here, right? You got one wave perpendicular to another wave, and then you got a traveling or propagating perpendicular to both of those waves. That's what electromagnetic radiation is. The theory behind this EMR came from a Scottish guy named James Clerk Maxwell. Okay, he knew already, this was established already, that a changing magnetic field would produce a changing electric field. And he hypothesized by symmetry. Physics is a very symmetrical discipline. When A causes B, then B will often cause A. We talked about that a little bit in the last unit, right? Electricity causes magnetism. Well then, why can't magnetism cause electricity? Maxwell hypothesized that by symmetry, a changing electric field would produce a changing magnetic field. This is critical. This is critical here. If you have a magnetic field that is constant and an electric field that's constant, the magnetic field will not produce an electric field, and the electric field will not produce a magnetic field. If you want magnetism, the magnetic field, to produce the electric field, then you have to have a changing magnetic field. And if you want the electric field to produce a magnetic field, then you have to have a changing electric field. Maxwell hypothesized that that was the nature of the propagation of this wave. The magnetic field that we have right here and the electric field, sorry, the magnetic field right here and the electric field that we have right here, like this, cause the electric field right here and the magnetic field right here, which in turn cause the electric field and the magnetic field, which in turn cause the magnetic field and the electric field, and so on and so on and so on. So what you get is over here with the source of this electromagnetic radiation, the source of this energy, which is actually an accelerating charged particle generating a changing electric and magnetic field, get this changing electric and magnetic field, which causes another changing electric and magnetic field over here, which causes another one over here, which causes another one over here, and so on. It's kind of self-sustaining. Now, when this one produces this one, well, the first one disappears, right? Because the energy has moved over here. Then this one, this energy is gone now. And then this one, now this energy is gone. Unless the particle over here that's causing it all is still accelerating and constantly replacing the energy that propagated or moved. So we got a changing electric field and a changing magnetic field generating more electric and magnetic fields, which causes the wave to actually move down this way. If we don't have this changing nature, this changing electric and magnetic field, then all we got is an electric field and a magnetic field, and nothing happens to it. Because it's changing, it can travel, it can move. And that's EMR, okay, the movement of this energy, this pure energy in this wave-like form, perpendicular to both of the waves. When it moves, when it propagates perpendicular, and it moves really, really, really fast. 3 times 10 to the 8 meters per second in a vacuum, which is about 1 billion kilometers per hour. That's fast. In fact, that's so fast that if we were to look at the globe, Halifax, Nova Scotia would be over here. Victoria, BC would be over here. Canada's a big country, right? Curvature of the Earth. I mean, if you were to look in a straight line from Halifax to Victoria and you could see really, really far, you'd never see Victoria from Halifax because the Earth would get in the way. The curvature of the Earth would literally get in the way. But let's say for a second you could turn a flashlight on in Halifax, shine that flashlight, and it would follow the curvature of the Earth, let's say, strike a mirror in Victoria, and then bounce back. And then strike a mirror in Halifax, and then bounce back to Victoria, and then back to Halifax, and so on and so on and so on. Let's say you could do that, which of course you can't. But let's say you could. If you could, then light would make about 30 of those return trips, Halifax to Victoria, Halifax, Victoria, and back again. About 30 of them in 1 second. That's how fast light travels. That's 1 billion kilometers per hour. Nothing can travel faster than light. It is the cosmic speed limit. Nothing will go faster than the speed of light. When you try to get something going faster than the speed of light, something crazy happens. It doesn't go faster, it gets heavier. You pump energy into it to make it go faster and faster and faster. Oh, all you're doing when you get to speeds approaching the speed of light is make it get heavier and heavier and heavier instead of going faster and faster and faster. So as you get infinitely close to the speed of light, all of your energy that you're pumping into it to make it go faster gets converted to mass instead of to speed. So you can't get anything going faster than that because the energy gets siphoned off to being converted to mass instead. Now, electromagnetic radiation, we've drawn it as a wave, right? 2 sinusoidal waves, the electric field wave and a magnetic field wave. Sinusoidal, changing in nature, caused by an accelerating charged particle. But what other evidence do we have to support the wave nature of this electromagnetic radiation? I mean, Maxwell's theory said this is what electromagnetic radiation looks like, but what real proof do we have that his theory is correct, that there is a wave nature associated with EMR? When Maxwell came up with his theory and had some evidence to support the wave nature of it, it all of a sudden looked like, all right, it's decided. Electromagnetic radiation or light is a wave. But you know, for hundreds of years, people have been debating whether it's a wave or a particle. It was finally decided, right? Well, for the time being, it was finally decided when Maxwell came up with his theory here. What's the evidence that we have to support the wave nature of EMR? Well, it exhibits properties of waves. There's certain things that waves, certain properties that waves exhibit, certain properties that are associated with waves. And if EMR exhibits those properties, then it must be a wave. Polarization first. I probably should have put that one last because that's the one that you haven't heard of before. Okay, let's look at the other three first. Diffraction. It's diffraction. You learned that in physics 20. Diffraction is the spreading out of a wave. You guys remember that you had something like this, an opening, and you got these water waves or whatever waves that are coming towards this opening. Some of it goes through like this, and then what happens after it goes through? Starts spreading out like this. Diffraction. That's a property of waves. In EMR or light, when I say light, I mean EMR, right? Because we can't see all kinds of EMR, but we still call it light. Just because we can't see it doesn't mean it's not light. Right? Radio waves are a type of light. Gamma rays are a type of light. When light comes upon this opening, goes through, it spreads out, it diffracts. That's a property of waves. But since light exhibits that property, then light must be a wave, right? Interference. You guys remember interference? You got a crest meeting a crest, or a trough meeting a trough. You get constructive interference. A big crest or a big trough. But if a crest meets a trough, they cancel. That's destructive interference. It's a property of waves, but light or EMR exhibits that property. So light's got to be a wave. You know that you can have constructive interference for light? If you have two crests coming together, you get brighter light, or two troughs, you get brighter light. If you have a crest and a trough coming together at the same place, you get destructive interference. There's nothing there. They cancel out. Refraction was the bending of a wave when it goes from one medium to another. So here's your boundary, let's say between water and air. You got a little, you're playing golf and you hit a golf ball in the water. The golf ball's right there. Well, when light coming off the golf ball hits the boundary between the air and the water, the light bends. That's refraction. That's why, by the way, the golf ball appears to be in a different spot than it really is, because the light has bent it. You guys have all seen that picture of, or even done this, with the pencil in the water and the pencil appears bent, right? Why? Because the light coming off the pencil bends when it hits the water-air boundary. That's refraction. Happens because of a change in speed. The wave slows down or speeds up when it goes from one medium to the other. It's a property of waves, but it's exhibited by light, so light must be a wave. Polarization. This is the one that's new to you. Polarization is a filtering out of components of waves. I'll give you a little analogy here. Let's say we have a piece of plywood with a horizontal slit in that plywood, just a narrow horizontal opening in that plywood. Let's say we've got a rope that we're flinging back and forth like this to produce a sinusoidal wave in the rope. So we can do it like this and produce a wave like this, or we can do it like this and produce a wave like this, right? Or we could do a diagonal and produce a wave like this, whatever. Okay, depends on how we fling it, right? What the wave ends up looking like. Let's say we take this piece of plywood with this opening in it, and we fling the rope vertically like this. So fling it up and down like this. How much of this wave, this vertical wave, goes through this horizontal opening? 0. The wave would completely die. On the other side, all you'd have would be a flat rope. But if you took the rope and flung it like this, horizontally, so that the wave went like this towards that opening, how much would go through? All of it. This is polarized horizontally. It allows only the horizontal component to go through. If I was to flick the rope at an angle like this, how much of it would go through? The X component of that wave would go through, and the Y component would be filtered out. It's horizontally polarized. If I had a vertical piece of plywood with a vertical slit in it, or a vertical slot in it, what would happen if I put the vertical wave through? It would all go through. Horizontal? None of it would go through. Diagonal? Well, the vertical component would go through then, and nothing else. The horizontal would be filtered out. What if, and then I'll answer your question, what if I took polarizing filter 1 and put it right on top of polarizing filter 2. What would happen then? Nothing would go through, right? It's completely 100% polarized. You flick the vertical wave, okay? Polarizing filter 1 was horizontal, I think, wasn't it? Yeah. So filter 1 would allow only the horizontal to go through, but then that would be stopped by polarizing filter 2. If you put a vertical wave, then it would be stopped right away by polarizing filter 1. So in the end, both horizontal and vertical would be filtered out, and it would be completely polarized. Polarized, if you have a decent pair of sunglasses, they're polarized. Okay, that filters out a component of the sunlight, okay, and cuts glare. Okay? Polarizing filters filter out components of waves. Now, polarization is a property of waves, but yet, I said we use them in sunglasses. Light exhibits polarization, so it must be a wave. 4 properties exhibited by or 4 properties of waves that are exhibited by electromagnetic radiation lend evidence to the notion that light is a wave. Question? All right, let's talk about the types of EMR now. You've already heard these, right? When you listen to the song at the beginning of your class, you heard the 7 types of EMR. You probably remember them. In order of increasing frequency. So frequency goes up as we go from left to right. Energy goes up as we go from left to right. Wavelength actually goes down as we go from left to right. So this song, if you remember that song, you're going to remember them in terms of increasing frequency, increasing wavelength, or increasing frequency, increasing energy, or decreasing wavelength. They are radio waves, microwaves, infrared, visible light, which is made up of red, orange, yellow, green, blue, indigo, and violet, ultraviolet, X-rays, and gamma rays. You will have to be able to rank these. You will have to identify the order of these at some point in terms of increasing frequency or increasing wavelength or decreasing wavelength or whatever the case may be. I want you to remember that song, and I want you to write out the spectrum as you see it on the board right here. And if you have to identify it in terms of decreasing frequency, then just read backwards on the list. Or increasing wavelength, then just read forwards on the list. What the good news or the bad news? The bad news first? Okay. The bad news is this. There are 7 types of electromagnetic radiation here. Each of these types of EMR have a range of frequencies, in a range of wavelengths, in a range of energies associated with them. We need to be able to, come test time, given a certain frequency, certain wavelength, or certain energy, identify what type of EMR it is. In other words, we need to know, in one way or another, 21 different ranges of numbers, of frequencies, wavelengths, and energies. If you're anything like me, you would have no hope of memorizing 21 different ranges. I would just say, I give up. I'll miss that question. The good news is, we only really have to memorize 3 of the 21. And I think that's manageable. Okay, if I can manage that, then you guys can manage that. I want you to memorize, and there's no other way around this. You have to memorize that microwaves have a frequency range of 10 to the 9 to 10 to the 12 hertz. You must memorize that. There's no little mnemonic device that's going to help you to remember that microwaves are 10 to the 9 to 10 to the 12 hertz. You just got to remember it. In addition, you must remember that X-rays have a frequency of 10 to the 17 to 10 to the 20 hertz. Once again, there's no way around that. You've got to memorize that. Finally, visible light, which is drawn as a wider range, but it's actually a very, very narrow range of EMR. The frequency range of visible light, it's all in the 10 to the 14 range. Because it's so narrow and because it's the type that we can physically see, we're actually quite specific with the frequencies here, more than we are for microwaves and X-rays. The frequency range of visible light is 4 times 10 to the 14 to 7.5 times 10 to the 14 hertz. Now you can imagine if you're given a question where you find the frequency of a certain photon of light to be 10 to the 18 hertz, what is it? X-ray, easy, right? If you remember the range of X-rays. If it's 10 to the 11, what is it? Microwaves. If it's 5 times 10 to the 14, what is it? Visible light. Easy if you memorize those three, right? But what if you get a frequency that's 10 to the 16 hertz? What is it? You don't have to memorize it. That's ultraviolet. If it's in between visible light and like X-rays, it's got to be ultraviolet. If I got 5.5 times 10 to the 7 hertz, what is it? Radio waves. If I get 10 to the 22 hertz, what is it? Gamma rays. So memorize these three and then figure out the other four. Got it? Okay, so we've learned 7, but we've only had to memorize 3. Now, what if you're given a wavelength? What if you're given a wavelength of, let's say, I don't know, let's say the wavelength is 6 times 10 to the negative 7 meters. What type of EMR is that? Well, we haven't memorized any wavelength ranges. We got to memorize 3 wavelength ranges? No. What we're going to do is use an equation from physics 20, V is equal to F times lambda, rearrange that to solve for frequency. You guys remember that equation from physics 20? What's the speed again? Speed of light in a vacuum is? It's a billion kilometers per hour, or 3 times 10 to the 8 meters per second. Divide that by 6 times 10 to the negative 7 meters. And what do we get for frequency here? 5.0 times 10 to the 14 hertz. What is it? It's visible light. And how do we know it's visible light? Because it has a frequency in the visible light range. We can be given any wavelength, and from that calculate the frequency, and then from that compare it against the 3 ranges that we memorized, and now identify what type of EMR it is based on its wavelength. So now we've got 14 different ranges that we've looked at. How many have we memorized? 3. We're going to do something very similar to that for energy as well, but we're not going to do it yet. It's going to use an equation. We're going to find from that equation the frequency based on a certain energy and then compare it against the 3 ranges that we memorized. But the equation won't make much sense to you right now. So we'll wait till later on in the unit to give you that equation. Right now, you can just trust me that although we have to be able to know 21 different ranges, the last 7, you'll learn the specifics as to how to do that a little bit later on in this unit. Okay? We can do it though without memorizing any more frequencies or any more wavelengths or any more energies, just calculating frequency from the energy. Yeah, go ahead. Yeah. All right, there we go. Now, we have to identify what causes each type of EMR. We've got the range of frequencies and wavelengths and energies. We know that in the end, visible light is the exact same thing as X-rays except for the frequency and except for how it's caused. If you were to look at visible light and scrunch it together, it would look exactly the same thing as X-rays. If you were to look at X-rays and stretch it out, it would look the same as radio waves. What causes them, though, is a little bit different. Generally, they're all produced by accelerating charges, but specifically, we have different mechanisms for producing each of these. Radio waves and microwaves are both produced by what we call oscillating electric charge. What does the word oscillating mean? Yeah. Sorry? Moving, yeah, but more specific than that? back and forth. Yeah, repetitive, moving back and forth, back and forth, back and forth. Oscillating electric charge, electrons or some other charge going back and forth, back and forth. We have that in our house, right? As we plug something into the wall and it draws an electric current through the wire, there's oscillating electrons going through that wire, back and forth, back and forth, at 60 times per second. In fact, the electrons moving back and forth in the wire in your walls generate radio waves. It's low intensity radio waves, very low intensity radio waves, but radio waves nonetheless. You ever driving on the highway and listening to the radio and get to the best part of the song or the best part of the game you're listening to, and you drive under a power line that goes over the highway and your radio cuts out? Why does it cut out? Well, those power lines carry electrons back and forth, but they're much more high intensity than the power lines in your house, right? Which just have little wires carrying a few amps, right? They generate much higher intensity radio waves. Still not enough radio waves to go from Okotoks to Calgary, but enough to go from the power line to your car, right? So what does it do when those radio waves that are generated there get to the antenna of your car? Well, they interfere with the radio waves that you're trying to listen to. So you get interference. So you don't actually hear anything because it's just interference. It's white noise. Oscillating electric charge. Infrared, visible light, and ultraviolet. Infrared, which is infra or below red. Ultraviolet, which is ultra or above violet. That's where the names come from, right? Infrared, below red. Ultraviolet, above violet. All three of those are produced in a similar mechanism. If you've taken chemistry, you might be a little bit more familiar with this. We'll call it electron transitions in atoms. If an electron is on a higher level than it wants to be, and there's a vacant level down closer to the nucleus, then the electron rushes in to fill that vacant level. It's kind of like when I used to go to Flames games back in the 90s, and there was 12,000 people at a game. I'd spend my $8 to go sit in the sport check zone, and I'd see a vacancy in the second row, and I'd go sit there. I'd rush down to fill in the vacancy. Okay, that's what electrons do. They fall down, they rush down to fill in the vacancies. But as they do that, they give off electromagnetic radiation. They give off light in the form of either infrared, visible light, or ultraviolet. Occasionally, X-rays can be produced in that way, but usually it's these three. To get an X-ray produced by that mechanism, it would have to be a really big transition. It would be like me being in the very, very top row of the sport check zone, going to row 1, ice level, right? The biggest transition that I could possibly make. Okay, might make me release an X-ray. X-rays are normally produced by rapidly decelerating electrons. You go to the dentist and get an X-ray, right? They give you a couple X-rays once every couple of years at the dentist. They don't do it every time. Every couple of years, though, you get an X-ray at the dentist. The lady or the guy that's the hygienist comes in and says, yeah, it's your turn for X-rays this time around. So they put these cardboard things in your mouth, in between your teeth, and you got to bite down on them. Then they put this thing up beside your mouth, and they say, you ready? You're like, yeah, it's all good. And then they run away and hide behind a wall. Ever wonder how it's safe for you but not safe for them? Well, they'd be exposed to hundreds of them a day, right? We're exposed to 2 of them every couple of years. Our body does a very good job at repairing itself from X-ray damage. Every X-ray you get does damage. Every single one of them does damage. But your body does a really good job at repairing itself if you don't get too many of them. If you get too many of them, then the damage is done quicker than the reparations are done. So if you're a hygienist and get 100 of them a day, your body's not going to repair itself quick enough. If you're like me and get 2 X-rays every couple of years, then my body has no problem repairing itself quicker than the damage is done. How do they make those X-rays? That's your question in just a second here, okay? How do they make those X-rays? Well, they have an X-ray tube, which consists of an electric field that accelerates these electrons to incredibly high speeds, like 10 to the 7 meters per second. And then we just smash the electron into a target, and it stops instantly almost. It had kinetic energy. Kinetic energy's got to go somewhere. That kinetic energy goes off in the form of an X-ray photon. So X-rays are released. Kinetic energy is converted to X-ray energy. Question? Last one, gamma rays. Gamma rays are produced by nuclear decay. And when we say nuclear decay, what we really mean by that is a situation in which matter gets converted to energy. A nucleus splits up. An alpha particle is released, or nuclear fission takes place. A nucleus splits up. Matter is converted to energy in those situations. Matter is converted to energy. That energy goes off in the form of gamma rays. Again, ionizing radiation, more ionizing potential, in fact, than X-rays have. Gamma radiation is used often all kinds of places, sometimes not so good, sometimes in a very desirable situation, right? Cancer treatment. Okay, if anybody's ever heard of radiation therapy for cancer treatment, that's what it is, which differs from chemotherapy, right? Chemotherapy is a concoction of drugs. It's chemicals. Chemotherapy. Chemical therapy. It's drugs. And chemotherapy takes all kinds of different forms, right? Somebody gets chemotherapy, somebody else gets chemotherapy. It doesn't mean it's the same thing. It's just one concoction versus another concoction of drugs. Radiation is completely different. Radiation therapy is gamma rays, which are, by the way, produced at a hospital. You can't truck gamma rays in. You truck radioactive material to the hospital, and then the radioactive material decays, generates gamma rays, and then they get fired at the tumors. Gamma rays do damage to cells, right? So what do? We focus them at the tumor and try to damage the cells, try to damage those cells. The only problem is, hey, those tumors are inside our body, right? So aren't they going to damage the healthy cells on the way to it? Well, here's what they do, actually. It's kind of ingenious. They take a pretty low intensity gamma ray beam, zap it at the tumor. Then they take another one from a different angle, zap it at the tumor. Take another one from a different angle, zap it at the tumor. So we do some healthy damage at every entry point, some damage to healthy cells at every entry point. But they intersect, all those beams intersect where? At the tumor. So we get essentially constructive interference at the tumor. So that's where we do a lot of damage, is at that one spot. And they try to do some damage around it as well, just in case there's any stray cells around it.